I don't know if that's, is it better now? No. Okay, so yeah, so first before I start, this is a joint work with a grad student from Berkeley that I work with, Daniel Freeman. And before I start also, I saw before that there were some, hiring advertisements for university. We're also hiring. So this is basically a new group that we have created at Courant that tries to do math in the interface of data, machine learning, and statistics. So check out our website if you're interested. Okay, so what is this talk about? This talk is about, it starts with a very, the setup that I will be talking about is I would say like the classical machine learning setup, right? Where I will just define you some energy function that corresponds to the problem that you would like to solve in theory, right? Which essentially means that I have some data that is following some distribution, and then I just want to solve a prediction or a classification, prediction, regression task, right? And I have a way to penalize how well my model does, and in practice, we don't know this function, right? We can only query an estimator of this function by basically replacing the distribution by some empirical distribution, right? So this is and before, because we want this optimization to be telling us something about this function, we typically think about ways to penalize the model somehow. And my friend and colleague Ben Recht always starts his talks by saying that in machine learning there's a fundamental theorem of machine learning, right? Which is a theorem that the statement is the proof, right? Basically what it means is that how well I'm going to do for a given set of parameters, I can think about this error as a combination of two, right? How well do these parameters do in the training set, right? The training error, and how well, by how much I can basically bound the difference between basically the population and the empirical loss, okay? And so there's a long history of techniques and a lot of very, very interesting and nice work trying to essentially control, so on the one hand, use optimization, like become better optimization to make the first term smaller. That's the thing that we can do with our algorithm, and then try to do some math and to try to come up with a bound to basically for the second term, right? So we can say something about the generalization of the model. And something that also was very influential is that you cannot think about this problem by abstracting the optimization, right? The algorithms that you use to come up with these functions are really from the integral part of this trade-off, right? And this is something that was started, or like one of the very inspiring works was this paper by Léon Boutou and Olivier Bousquet. And so in a sense, I said that there's some theory, right, that tells us how these two terms interact. But in practice now, let's go back to reality. Let's think about the problem where we have a deep neural network, right? And we have image classification as the problems that we saw this morning. So how well does this story play when you have these deep networks in the mix? So what it turns out is that the best way we have right now to control this generalization gap has it's an empirical statement, right? But it has two main ingredients, right? One is that you have to rely on stochastic optimization, right? And right now, the best explanation I know about it is something that Léon Boutou always says, right? Is that when you do stochastic optimization, you are kind of adding noise to the energy function that you care about that is of the same nature, of the same distribution as basically the mismatch you have between the population and the empirical loss, right? And probably Francis back tomorrow is going to tell us maybe, I don't know. No, okay. So okay, but you have here an expert in the room that can tell you much more about this thing. And the other thing that is maybe a bit counterintuitive, right, is that another technique that, if you want like a recipe to make this thing work, you have to make the model as large as possible. Okay, so this is what? It's by no means predicted by the previous theory. Okay, so in other words, you have to try to put more layers, every layer more parameters, and there's a very nice empirical work in the recent ICLR where they really, through very systematic and large-scale experiments, they really figure out that, whatever regularizer you have learned that is basically the best at generalizing, you replace it by just a larger model, it's going to generalize better. And so this is just another highlight that there's very fundamental interplay between how my ability to optimize a complicated non-convex function and the ability of the model to generalize, right? So basically, what it turns out is that by making the model large as possible, we are basically doing something on the optimization side that is helping indirectly generalization. And so this is in this talk, what we will try to address is more on the second part, right? So basically, we want to understand how over-parametrization, understood as the fact that you just make the model larger, is affecting your energy landscape, right? Basically, the optimization that our algorithm is going to be facing. And so we have basically two sub-goals, right? First is that we will just concentrate on very simple topological properties of this landscape. We'll see what they mean and why they are interesting. And then we're also going to introduce a tool, like an algorithm if you want, that you can use in your current data set and your current model to kind of diagnose, like to say something a bit more rich than just a topology, right? Try to get some geometric information about these energy landscapes. Okay, so this is part of the line of work that is now growing and growing. So this is just the best I could summarize in one slide. So one of the papers that made the big splash some years ago was the paper by Anna Shoromanska, Gérard Benarous, and Yann Lecan, where they kind of introduced an analogy, right? They tried to approach this problem by introducing basically energy landscapes from statistical physics, so like spherical spin glasses, and through a number of very, let's say, like a number of assumptions, they kind of created this analogy, and that was a kind of motivated a lot of people to, study this problem and perhaps do a bit, go a bit more, like do a bit less assumptions to try to say something a bit more precise. And there's some follow-up work by Levin-Sagan, etc. There's another line of work that tries to use tensor factorization to try to understand how optimization of deep neural networks works, and basically how can you tame or control the non-convexity of the problem using ideas from tensor factorization. More close to what we are going to do, there's some works by Ohad Shamir and his colleagues in Israel, where they really start to focus on this regime where the number of parameters is basically growing faster than in their case the faster number of data points. And there's some follow-up nice work by also people at Columbia and Le Song. And then more recently, there's also ideas that come from, again, statistical physics. And there's this nice work by Patrick Chodari from UCLA, where what they are trying to do is not only trying to understand this loss surface, right, but also how by changing the algorithm that I use to optimize, can I indirectly change the loss surface, right? And there's this also this idea that comes from statistical physics called the local entropy method, where there's these ideas that are now being tried and explored in this context. Okay, so the first thing I wanted to convince you is something pretty obvious, right? Is that it's not because we are in a non-convex world that we cannot optimize things, right? I mean, this is a completely trivial and low-dimensional example of a function that is non-convex, but if you just do full gradient descent here, you converge to the global optimum, right? No problem. And there's also like this class of functions that is called quasi-convex that basically formalize. I mean, it's probably like it's a relatively large family that formalizes this property. Of course, there's a lot of ways where. So here's another example, right, of a function that is non-convex, and where I have no trouble to get to the local optimum. Is a function that has some symmetries encoded, right? And here you can see why this might be relevant in the context of neural networks, right? Because what happens is that if I have a function that is defined over some maybe weights of some neural network, right? You know that if you take the neural network and you do some permutation of the rows and the columns, right? It's exactly the same model, right? So you have a model that by construction, the loss surface is going to be symmetric with respect to some group. If you're lucky, the group can be continuous, but the group certainly contains some discrete elements, right? And so here, this is again a setting where that we'll have to understand. Okay. So what is basically the analytic tool that we are going to just explore here? Is just think about the loss surface that I described before as essentially just think it as a representation in terms of its level sets, right? So now what we are going to study is the properties of the sub-level sets, right? Basically the set of points in parameter space where the loss is smaller than a certain energy value, right? And so the first thing that we can study, just to try to make the problem as simple as we can, is that, okay, first let's think about just basic topological properties of these level sets, right? For every u, let's try to understand these level sets. And in particular, we are going to just query something very like a trivial topological notion, that is how many connected components do these level sets have, right? For every energy value, how many connected components these level sets have. So why is this an interesting question? Well, because you think like if you ask the question in a convex world, the answer is trivial, right? The number of connected components is always 1, right? Because by definition of a convex function, I can always basically connect any 2 points that have the same energy, right? And so another obvious property is that if the condition is verified, right? If a loss surface has level sets that have single connected component for every energy value, then the function cannot have a poor local minima, right? I mean, if you think about having what it means to have a poor local minima is that I have some point in parameter space that is surrounded, right, by points in parameter space where the loss is larger, right? So it means that basically you cannot escape, you cannot connect these points with the other points that have the same energy. Okay, so here's basically using this definition of local minima that is strict. So I don't care about the degenerate case with saddle points in this definition. And of course, as I said, this definition is too strong, right? It's stronger than the lack of poor local minima, right? I mean, you can have functions where there's no poor local minima, but the level sets, if you cut here, right, you have 2 connected components, right? So anyway, let's stick with that notion and see what can we say. So following the trend that is not just authors in deep learning, but the trend in many areas is, okay, maybe let's try to simplify the problem, right? Let's try to first study a problem that is simpler than just the original one, right? And so one way to do that is to get rid of the nonlinearities. Why would you do that? I mean, this is think about this just for academic purposes right now, just for the sake of understanding something, right? I mean, I don't see any. Well, I mean, after I said this a couple of times, some people told me that it's not so stupid as that. I mean, this problem might be interesting in some regimes. For example, if you want to do matrix factorization, but in the context of neural networks, there's no reason why you would want to solve this thing, right? But let's stick with that and see, what can we say about this function? So it turns out that this problem is like it's a multilinear regression problem, right? And it's easy to see that this problem is non-convex and non-concave, right? You have these basically the sun interactions between the terms. They basically they create like a lot of saddle points. But it turns out that you can kind of control the saddle point structure, right? You can prove that if you have a critical point, either it's a global minima or it's a strict saddle, right? Which means that essentially you can always escape poor local minima. And this is under some assumptions on the data and basically the properties of the covariance structure. And this has been generalized by several authors. The one that I like is this paper where they also reveal that if you work in the ResNet, if you use the residual network decomposition, as some colleagues said this morning, somehow this picture gets a bit more clear. And so what can we say about this problem with basically our definition? So what we show is that essentially if you parameterize the network just slightly, just go slightly above the minimum number of either input or output parameters, not only you have poor local minima, but you have completely connected components, right? So basically if you over-parameterize the model, but just a tiny bit, then there's no, not only there's no poor local minima, this we knew it already, but you have only one connected component. And this doesn't assume anything about the data, right? This is true for any, basically for any covariance. And this is also, we can also incorporate something that is a bit closer to reality, that is not just basically the risk minimization, but also basically the regularized case, right? Where you have this, if you incorporate this rich regression, you can also guarantee this. What else? And this, in a sense, after you understand this, it's clear that this is really an artifact, right? That as soon as you put a nonlinearity in between, this problem becomes basically just a sort of an exception, right? In the sense that if you have nonlinearities, then you can always play the adversary, right? So if you fix the architecture, there's always a distribution that will not satisfy this property, okay? Which is it's a thought experiment, right? It's never the case that you first choose the architecture and then someone builds a distribution that is going to break your architecture, right? It's typically the opposite. So just very briefly to, to see that there's really no mystery in why this result is true. So because we are in this in this game of just establishing connectedness, right? Our goal is just to, given 2 points in parameter space, we just need to construct a path, right? And the path just need to satisfy that the path cannot escape the sublevel set, right? So basically the energy along the path has to be upper bounded by the energy that it has in its extrema. So this is just done by induction, right, on the number of layers. And so if you think about the key step is what happens with have 2 layers, right? If you have 2 layers, the idea is actually pretty simple. You just lift the problem. Basically, you just you just assume that there was only one linear operator, right? But it's just the product of the 2. In that case, the problem is convex with respect to these lifted parameters, right? It's basically a linear regression problem. If you have only one layer, the thing I'm saying is completely trivial, right? So you can, if you have a convex loss, a linear path stays in the level set, right? By definition of convexity. And so once you have this path on the lifted domain, now the goal, like the job that you need to do, is to factorize this path, right? You know that in the beginning and in the end, these matrices are the product of W1, W2, right? So basically what you need to do is to factorize this path as a product of 2 matrices that satisfy a number of conditions. And at the end, the main mathematical tool here is that the only thing that you need to do is realize that if you have the group of invertible matrices, right, basically the group of matrices that have an inverse, this group has 2 connected components, right? The ones that have determinant that is positive and the ones that have determinant that is negative. So if you just have, that explains why you need to have just one extra, if you just have one more dimension over like a redundancy, then you can basically jump from one connected component to the other. That's basically the story. Okay, so natural question, right? How much redundancy are we paying to basically establish the fact that the level sets are connected and not just the original problem of having poor connected components, right? So you could ask, well, you are proving something that is stronger than the property that like someone who does optimization would be interested on, right? So how much are we paying? So it turns out that in this case, we can show quite easily that this condition that we need to be a bit over-parameterized is not needed anymore, right? So basically what you show is that basically just by repeating the same proof but on the quotient space, right? Now every parameter, you just consider it on the Grassmannian manifold of basically subspaces, right? You basically quotient out the space by any invertible linear matrix. Okay, so you do the same, and we have this update like this. So this is some work that has been like a pioneer. Well, it has been done with our PhD student Luca Venturi, and together with me and my colleague Alfonso Bandeira. So what we have is basically a generalization of the previous results on basically multilinear regression, right? And now, I mean, something that is not very surprising, right? That this problem has no poor local minima, never, right? Okay, but here this is still a linear problem, right? It's not very interesting. So what we go, I mean, our goal essentially is to go from from linear to the real case. And I will show you the results on the ReLU, but before, along the way, there's a very I would say natural nonlinearity that is kind of instructive, right, to understand basically the proof technique. That is essentially consider that you just use as a nonlinearity the square. Okay. Not a lot of people in practice use this. I'm pretty sure that with the modern technology of batch normalization, like a very well-tuned stochastic optimization, it should not. I mean, probably it would not become very, very bad in, let's say, modern image classification. But I don't mean, just for the moment, think that this is a kind of a nonlinearity that is there that will hopefully help us understand the real case. So how do we deal with this problem? So again, the idea, so like the idea of the proof, or the idea of the technique, is just to kernelize this problem, right? Basically, if you have a problem where you have one hidden layer that is quadratic, it can be seen as a linear layer, right? Where you have lifted the problem, right? Basically, now it's linear in terms of the outer product of the data, right? It's linear in the outer product of the data, and now your linear coefficients are not just weights as before, but they are this kind of funny rank 1 matrices, right? But nevertheless, you can use basically this very this relatively simple formula to have basically the extension of before, right? Is that now if your hidden layer has a size that is now quadratic with respect to the input dimension, right, and the constant here is relatively small, then you have the same properties before, right? This optimization problem, so this energy landscape problem has only one connected component for every energy value. And again, by applying a simple induction, you can basically generalize the result to arbitrary number of layers. Of course, there's no free lunch here, right? I mean, as you keep adding layers, you have to keep making the size of the hidden layer larger and larger, right? It grows in a relatively ugly way here. Okay, and so one question that we are wondering is can we make this rate a bit better by basically exploiting the group symmetries, right? Again, as before, here we are shooting for a problem that is very strong, a property that is very strong. Okay, if we just care about lack of poor local minima, can we improve the rate? So right now we are just gaining on the constants, right? We just went from 3 to 1. Not very exciting, not very impressive, but that's an open question that we're wondering. Okay, and besides the quadratic case, what we also proved with Daniel is so we also studied the ReLU case, right? So the ReLU case, for those of you who are not familiar, the ReLU is this funny thresholding operator, right? Is the max between, well, it's max between 0 and z. So here we consider a setup that is not the full general setup, but it contains already one hidden layer, which is you could consider it deep, because we are learning basically, we are learning both W1 and W2, and we are basically projecting the first layer coefficients to the sphere, just because because there's this homogeneous symmetry, so this doesn't lose anything. And so here's our result. So here, as opposed to the previous results, right, that established that for a given sufficiently large neural network, then there was only one connected component. Here, the story is slightly different, right? So here, the story, what we are able to show, is not exactly that we can connect that the level sets are connected, but for any 2 points in parameter space, we can construct a path, right, where basically that almost stays in the level set. Right, what it means that almost is that the energy price that we need to pay, right, basically it will stay in the level set, but we might have to accept some epsilon. But this epsilon goes to 0 as the size of the network increases, right? So basically what it means is that asymptotically, right, if this number is sufficiently small, well, you can say that essentially it stays in the level set. Yes?
N is the input dimension?
N is the input dimension.
Exponential dimension?
Yes, very bad.
Right.
Very bad. Yes, very bad. But I think it's not surprising, right? Because I mean, Francis is really nailing the problem, right? Is that here what we are establishing is something that essentially, what we are kind of using is that, well, if you have a neural network that has sufficient, like enough hidden, so the size of the hidden layer is sufficiently large that I can essentially encode every possible half space in dimension n, then I can essentially move from any point to any point, right? But if you think how many half spaces do I have in dimension n, too many, right? It's an exponential number. So that's why we have this very bad looking rate. Okay, and so and of course one of the natural questions that emerge here is that maybe this is an artifact of the fact that we are using a nonlinearity that maybe a couple of engineers or a couple of computer scientists came up with that seem to work well on MNIST, but maybe it's not the only one, right? Maybe there's nonlinearities here that are maybe a bit more smooth, right? That look closer to the quadratic case. Maybe I can basically use a Taylor decomposition of the nonlinearity, and maybe based on the decay of the Taylor coefficients, I can recover a rate that is not exponential.
Want to get like square root of n or n over 2 instead of n?
Yeah, that's well. I mean, it's I don't know. That's an interesting question. I'm more now, depending on the day, I'm a bit optimistic, right, that I can get closer to the square. But yeah, I don't know. Maybe we can discuss offline about this. And related to that, I mean, when I'm optimistic, I have basically asked this question, right? Can we rethink about optimizing deep neural networks from the perspective of kernel, right? As someone who, kernel theory, which is something that I have to say, the students that are now doing machine learning, at least deep learning, they have no idea what kernels are, and this is really we have to do something about it. And so basically the technique that I've been telling you, right, is really that simple, right? It's basically you have a model that is nonlinear that contains parameters at every layer, and these are basically the parameters that the algorithm sees, right? The parameters on which you take gradients, right? With respect to which you take gradients. But there's another way to look at this thing as an operator, right? This is basically an operator that is mapping images to whatever, right? Targets. And as an operator, you can see it as a point, an element in some functional space, right? And and this is the thing that you can associate it with basically this strange mapping, right? You can think about this operator as maybe basically taking some canonical set of features that might be infinite dimensional, and then applying an appropriate linear combination of these high-dimensional features, right? And this is the vision that is formalized by basically this notion of reproducing kernel Hilbert space. And so actually there's some recent works that now try to basically apply this machinery to study deep neural networks. And so here I'm just citing a very nice work by Julien Meral and his student Alberto Bietti. Another recent paper by Martin Wainwright and Percy Liang. And then I think Francis might talk a little bit about this tomorrow with their values. So basically these are ideas that in essentially are underpinning what I'm saying, right? But they formalize it and they can maybe bring us a bit farther. And so one of the things that in particular is interesting to me and to the community is that, as I said, you will be taking gradients in that space, right? And when you take gradients in that space, you might be doing funny things in that space, right? And so understanding how can you understand the behavior of SGD in the neural network parameters in terms of the corresponding RKHS is something that is it's like a potentially interesting tool to understand why SGD works well. And there's a little bit of progress in the direction, some work by Natis Rebo, where he's also making progress in the related problem of matrix factorization. Okay, so this is for the theory, right? Or like at least this is some of the things that we have able to prove, like to show like analytically. Now the next thing, these are results that are of course asymptotically, right? They are just a bunch of upper bounds. I mean, if you show this to a practitioner, I mean, what is the use of this, right? I mean, there's no way you can relate this to a practical problem. So in that direction, the next thing that we are trying to do is essentially try to say something a bit more precise about why the actual stochastic gradient descent is going to succeed or not in a real problem. And so, of course, being able saying that the level sets are connected is kind of a necessary condition for this algorithm not getting stuck, but it's far from being sufficient, right? I mean, the next thing that we try to understand is, okay, do we have level sets in deep learning that look like nice, convex, smooth things, or do we have level sets that are like crazy, high-dimensional, irregular structures like this one, right? So typically, I mean, our intuition, as I could check, is that our intuition in high dimensions gets pretty bad, right? I mean, many people tend to think that, in deep learning, you have crazy things like that, right? But so in a sense, that's what we try to can we derive like a diagnostic tool, like an algorithm that will help us to determine, where we are, okay? And so what we try to do is that now we are going to try to estimate geodesics of these level sets, right? So the way this thing will go is that suppose that you are able to sample 2 points from the border, okay? So this is something that you can take your favorite SGD algorithm, you can run it twice by randomizing the initial condition until you reach a certain training error, right? So this will give you 2 points here, and now what we'll try to do is to try to construct a path, right? And the construction of the path has to stay in the level set. And so once we have this path, perhaps what we can try to do is to find the shortest path, right? Basically the one that is as short as possible. And by accessing by measuring the length of the shortest path and maybe normalizing it by the Euclidean distance, we have a very simple diagnostic tool that will help us to understand. Well, in particular, if you are in this quasi-convex world, you should expect linear paths to be sufficient, right, to be geodesics. So how are we going to compute this algorithm? How are we going to find these geodesics? So very simple, right? We just ask for a path. Basically, it's just, of course, this path is going to be discretized in practice that stays in the level set and that minimizes basically the length, right? So we are going to do it with a simple dynamic programming approach where we start with the 2 points in the frontier, and what we try to do is now, can we find a new point, a new parameter, such that it stays as close as possible from the basically the linear, basically the average of the two, and the loss stays in the level set, right? So basically what we try to do is that first we try this point. Does this point in parameter space have a loss that is not larger than the one that we have in the extrema? If yes, that's done. Otherwise, we try to move a little bit around this point until we basically go back to the level set. Okay? Once we have found this point, we iterate the algorithm, right? Basically, we take this thing and then we break the point. Okay? Does it make sense? Of course. Okay. Okay, so we just repeat this thing, and now what we can do is that we can just run it on data, right? On problems, on models, and then see what happens. So here are some results, right? So basically, we can first, as a kind of a fine-tuning, just to double check that the algorithm is doing what we think it should do. We can start by playing it on toy low-dimensional regression problems, right? Where we kind of control very well basically the energy landscape, right? And basically, what we're able to see is that well, this is maybe not so interesting, but this is an interesting one, right? Is that here what we show is a picture where on the x-axis you have the energy level, right? And on the y-axis you have this normalized length, which is the length of the geodesic divided by the Euclidean distance, right? And so if the length was 1 all the time, what it means is that essentially the level sets of this problem are convex, right? And what you see here is that on MNIST it's interesting because up until you go to the state of the art, which is maybe 0.5. Okay, so here we trained the model until it was 0.7. Okay, using a off-the-shelf convolution neural network. What we see is that the level sets are not convex, right? But the amount of non-convexity is really small, right? It's like 4% non-convex. And in a sense, I like to show this thing because we always have this wisdom that MNIST is easy, right? Everything works on MNIST. So you can think that this might be like one quantitative way. It's like 4% easy to me, right? It's basically saying that. I mean, of course, it's a bit hand-wavy, but and then you can trade these things on more complicated things that are known to be a bit harder. Basically, you can use a Cipher10, which is an object recognition data set. You can use this. Here we use what was the standard CNN like 2 years ago, like 1 year ago. I don't know what the name was. But again, we observe the same phenomena. But here, what you can see is that indeed the level sets become a little bit more irregular, right? But what is remarkable, okay, in all these plots is that always we establish connectedness, right? We haven't found any practical example beyond the degenerate cases that we constructed ourselves, where the level sets that we explore are disconnected. Okay, so if you give me a real data set with a realistic network, 2 points in parameter space, I can always connect them with a path where the loss stays constant. And this is also true on this is a problem on basically character prediction. So this is we use here the networks that are like what's called LSTMs, which are a form of recurrent neural networks, the same phenomena. So essentially this is I hope I didn't go over time. No? Okay, perfect. So this is the last slide. And so what I try to show you here is a story where basically with this very simple, relatively simple analysis, we are able to say things that are perhaps surprising from a priori. The fact that maybe one would expect that as you look into these problems in practice, with a large network and a complicated object recognition problem, you would expect to really see the non-convexity in front of you, right? You would expect to see a bunch of different connected components. It's not something that we have explored. We have seen in practice. We have yet to see this thing. This is a bit less surprising, right? the fact that, of course, as you go deeper and deeper in the energy values, you start to see sets that are a bit more irregular, right? That's something that our algorithm is able to discover easily. More on the theory side, this is a question that might or might not be happening. I think that there's some interesting theory to be, there's some interesting ideas there that can connect well, can help us understand the behavior of these optimization algorithms. And some of the things that I'm currently wondering is that the beginning of the talk was really about what happens as we make the model size larger, right? So from the optimization and maybe from the things I described, what we know is that in terms of optimization, there's something that gets easier and easier, right? That's what we try to explain here. But we know that from statistics, right? There's a moment where we should start to see basically the overfitting phenomenon. At some point, we should start to basically pay a price by making things larger. So is this true? And can we basically construct or understand like a sweet spot? And then, of course, something I didn't describe here at all is that everything I said is independent of the algorithm, right? And as we know, the reality is not like this, right? In practice, we know that choosing the right stochastic optimization can make a huge difference in terms of the generalization performance. So this is again something that we would like to combine, right, with this story. So with that, thank you. And if you have questions, yeah, please.
For the last talk. Are there any questions? Then I make a start. So how does regularization play a role in your theory? Everything you said so far was without regularization, right?
So there's one result that includes the regularization when you have only one hidden layer, like two sets of parameters. Yeah. And there it's interesting because I use again one of the nice papers from Francis, where you have basically a variational characterization of the norm. So basically, this rich, like basically the rich regression that you see in this term, you have there's a variational. So you can see this as if you minimize over the parameters on this expression, you can control it with a norm in the lifted parameters. Okay, so this is I don't know if you're familiar, the nuclear norm admits this variational expression in terms of the Frobenius norms of the factors. So that's what we use to prove this thing for the linear case with the 2 layers. We don't know how to extend it. If you go from 2 layers to more than 2 layers, from what I understand from Francis, there's no simple way to use the same trick. So who knows?
Any other questions?
You showed the graphs for the stochastic gradient descent, and you said that maybe the algorithm could be a sensitive component here.
Yes.
Have you tried to change some parameters of the algorithm, like batch size, and see if the diagrams are qualitatively similar?
It's a good question. Yeah, so we tried basically to initialize one set of weights with a batch gradient descent and the other with stochastic. We could still connect. One thing that we didn't try, and I got like last time I gave the talk, someone gave this suggestion that I think could be interesting, is that right now we always initialize the algorithm with basically IAD Gaussian weights. Question is, can you have like an adversarial initialization, right? Can you, after the fact, come up with basically a way to initialize the algorithm in a spot that is probably away from like so. And again, this I believe that there might be some truth to that, because when you initialize from Gaussian ensemble, there's some concentration, there's something there that puts you in a very specific region of the space. So that's another direction that we could think of.
Any other questions? Let's thank Joan again.